Something I know I've been missing from my peripheral reviews is the ability to test the click latency. So having the open source latency testing tool on hand is pretty useful. For those that have one, here are the currently 3 ways you can test click or keypress latency with mice and keyboards. First up is the easiest, but also least accurate method, which is using the included microphone to listen out for the clicks. How you do it is pretty simple. Just place the microphone next to the switch you're going to hit, whether that be a mouse or a keyboard. Just have the mic right next to whatever you're going to press. Make sure you select either the keyboard or mouse options in the software and then start the test. You can then get clicking loudly, like, and also leave a second or so between presses to make sure they register, so like something like that. Once you've gathered enough samples, you can end the test and view the results. As for why this is the least accurate method, basically that click sound that you're hearing is only, or the board is listening for, is only emitted once the shell part of the mouse bottoms out. And so, especially with higher polling rate devices like this Viper 8K Hz, where the click event is sent out in under or about a quarter of a millisecond, the sound likely hasn't even happened yet, let alone the board recognizing it and triggering the timer. For 1000 Hz peripherals, the microphone mode works perfectly fine. But if you're testing anything with a higher polling rate, or you just want the utmost in accuracy, you'll need to use the 2-pin input. This input method lets you solder directly to the switch itself and capture the electrical signal that the mouse is registering. You will need to take the mouse apart for this, and you'll need a soldering iron and a multimeter to be able to check what pins you need to be soldering to. For most of the mice that I've tested, the central of the 3 pins is the switched pin, the one that you need to connect the signal wire to, the one with the sort of Molex sticker on it. And then the other 2 are normally connected to ground, although in some mice's case, like this glorious Model O Pro, you have only the top or the frontmost pin is actually soldered, the back one isn't, and so you want to solder the front one to the ground pin, the other pin of the 2-pin input. If your unit shipped before the 22nd of November, now last year, you will need to solder a 1 mega ohm resistor in line with the signal wire, like this. I fixed this in future versions or more recent shipped units by changing the internal resistor in here, and you can too if you'd like. It's an 0805 SMD package on R7. You can then start the test the same way you would with a microphone, except selecting the 2-pin input and get clicking. This should be considerably more accurate, albeit a bit more painful to actually get set up. And because that's quite a pain to use, I have one more option for you. At the moment, this is a bit of a bodge, but it's kind of the best of both worlds. It's something that RX showed me while discussing different test methods on GitHub, and in short, you'll need some aluminium tape, or in my case some tinfoil, and a crocodile clip. I'm using some tinfoil here with a lead soldered to it, and you'll also need an external power source. In my case, I'm using this Raspberry Pi. I'm basically just going to connect the tinfoil or aluminium foil to the 3.3 volt pin on the Pi's headers and attach this to the mouse's left click button, and then you have the ground pin of the 2-pin signal wire connected to the ground on the Pi. And then basically you take your signal wire and you tap it on your mouse button, creating a connection between the 3.3 volt supply on the foil and therefore on the mouse to the OSLTT unit. This works basically the same way, except you should get much more accurate results. I am planning on making this a more official test mode in a future version of the latency tool, but it's worth noting that it effectively reverses the inaccuracy of the sound or microphone test mode, as the board will detect the click before the mouse will. The switch has a certain amount of pre-travel essentially, and that's counted as part of the click time. Now, I would argue that this is the most real-world measurement, as it's basically measuring from the instant you start pushing down on the button to when the click is registered in Windows, but it does mean that it is counting some of that time when you're pushing on it, but the switch hasn't actually actuated. Just worth noting. I should also explain how this test mode in general works from a software perspective. As of version 0.9 of the desktop software, I now use a mouse and keyboard hook to detect the mouse or key down events. I specifically use mouse down or key down events as that's the first event reported and is the most accurate one to use. The mouse hook in particular is considerably more reliable than the event tracking in WinForms, so you should see a fair bit better accuracy on that front. Of course, if you have any suggestions for other ways that we can test peripherals, do let me know in the comments below or over on our Discord. I would love to learn more and improve the tool for everyone. Of course, if you're interested in picking up a latency tool, you don't have one already, you can head over to OSLTT.com where I make them available. I make them like literally in my house downstairs, made in the UK. So if you're interested in picking one up, feel free to head over there. You can also check out more videos on the latency tool and just generally peripheral reviews, monitor reviews, and a whole lot of other stuff I do on the end cards when they pop up in a second. And you can also subscribe if you want to stay up to date on tools like this that I'm making and obviously all the reviews that I'm doing as well. Otherwise, that's pretty much it. If you have any questions, like I said, feel free to leave them in the comments or jump over on our Discord. Otherwise, thanks for watching. Hope you enjoyed it. I'll see you on the next video.